Hi everyone, I'm Indian Nazmul Hassan, a PhD student at the University of British Columbia, Vancouver, Canada. Welcome to this antenna engineering webinar on AMC or Artificial Magnetic Conductor Design in HFSS. We'll be talking about its theory along with its applications and implementations in HFSS. Primarily, we'll be interested in finding its property of reflection phase. So let's begin our webinar. So this is a metal sheet. You all know that it has abundance of electrons inside it. So whenever an electric field is applied on it, the electrons are excited, creating the surface current. And we call this type of behavior conductivity. And we can characterize this sheet as PEC or perfect electric conductor. One important feature of this metal sheet is that it can block electric field, so no electric field can penetrate inside of this sheet. Now imagine a counterpart, a hypothetical sheet that can block magnetic field instead of electric field. Now that type of hypothetical sheet is known as perfect magnetic conductor. It's nothing but a counterpart that we have just demonstrated with the metal sheet. We can characterize this property of surface in terms of single feature called surface impedance, denoted as ZS. For the metal sheet, we have very low surface impedance, and as for the PMC, it has a very high surface impedance. Although in nature we don't have this instant or a ready-made PMC, but we can definitely mimic this behavior in terms of our own design or custom design. And we will be seeing in the later part of this presentation how we can mimic this property by using different mechanisms. Now moving on to the AMC part. So basically, what is AMC? Artificial magnetic conductor is a type of PMC or perfect magnetic conductor. Although that's a very idealistic situation, we call it perfect, but basically we can create this artificial magnetic conductor type of behavior with this surface. It's basically a periodic arrangement of this unit cell which has this similar or identical property. If you know about metasurface or metamaterial, you might have heard about its subcategory or subsets like FSSS or frequency selective surface. So AMC is subset of this metamaterial or metasurface. Basically, metamaterial is a 3D structure, and when you flatten this 3D structure, creating the 2D version of the 3D, having this planarity, we may call it metasurface. And AMC, like I said before, it's a subset of this superset metasurface. We also have another type of metasurface, or you can say unit cell split ring resonator, or SRR. Now let's move on to its application. Why is it so important to use AMC in antenna engineering? Well, if you imagine this metal sheet, which is basically a PEC surface, and if you have this normal on the surface and you shine a wave on the surface, that means there is an incident wave hitting on the surface. Then, since this is a PEC surface acting like a mirror, we will have this reflected wave going out. Now, by nature, this PEC surface will create this 180-degree reflection phase, or the reflected wave will be inverted 180 degree compared to the incident wave. So this is the property of PEC surface. Imagine what happens to this PMC. Now, PMC or AMC surface does not invert this reflected waves phase. So this is very important property of AMC. If you notice, the incident wave phase and the reflected wave phase are in phase. They are not inverted at all. So this feature is very important in the design of antenna engineering. Why, we will see in the later slides. Now imagine we have a patch antenna, microstrip patch antenna. You will know that we have a patch on the top of a substrate, and on the bottom we have this solid metal ground plane as denoted in this figure. Now what happens if you plot the radiation pattern of this patch antenna? You might notice these little ripples. So what causes this ripple? Now if you draw the current plot, the sinusoidal current on the patch, you might denote it with this green plot. Now as for the patch antenna's current, the ground is a solid plane, so it would generate the image current that's flowing onto the radiating surface, that means the patch. And since the thickness of the dielectric material is very, very low compared to the quarter wavelength, the image current is basically 180° out of phase. So if you plot the current flowing on the ground and on the patch, you would notice this 180° out of phase. So what happens if I replace this ground plane with AMC ground? Because we know that AMC does not change the reflected wave's phase. So by exploiting this behavior, we can prove that if we employ the ground as an AMC surface, then we would have the current on the AMC ground in the same phase as that of the patch antenna. So that would mean the radiation will not have that tiny ripples. So the radiation plot would be much cleaner. So these ripples are basically caused by this 180° inversion caused by the ground plane. So if you simply replace this ground plane with the AMC ground plane, then these ripples would be vanished and you will get a very nice radiation pattern. So this is one important application of this AMC with the patch antenna. We can also use AMC as absorbing surface or as a superstrate to increase the gain. And there are many other applications in antenna engineering with this AMC structure. Now let's move on to the property of reflection phase of AMC and how to determine the bandwidth of AMC. We can determine the bandwidth from the reflection phase plot. So along x-axis we have frequency, and along y-axis we have the phase of the reflected wave, which we call the reflection phase. It's basically an S-curve. It has an inherent shape of an S, elongated S. And if you notice, the 0° intersects the curve at point A, and at that particular frequency, the AMC achieves the resonance, and we called F0 as the resonance frequency of AMC. And if we further analyze this plot by intersecting the plus 90° and minus 90°, and we can see the 2 points intersect on these 2 particular points, and then determine the bandwidth between F1 and F2. So that shaded region is the bandwidth of the AMC, wherein the AMC does not invert the phase of the reflected wave. So that means within this frequency, whatever incident wave hits the surface of AMC, the reflected phase will not change. And further, if you notice, along very low frequency, the AMC has a reflection phase about 180°, exactly similar to metal. So from that, we can conclude that at very low frequency, AMC would behave as a metal, but at a certain frequency range, it would behave as an AMC, which does not invert the phase of the reflected wave. Now let's talk about the modeling of AMC, or the analytical model of AMC in HFSS. We can basically model AMC analysis in two ways. For example, we imagine AMC is embedded in a rectangular waveguide. So this is basically a waveguide. Inside the waveguide, we have put the AMC at one end. And then, by a definition of the waveguide, the electric field and magnetic fields distribution would confine the wall of the waveguide as PMC and PEC on these two ends. And on the other side of this waveguide, we would be launching the wave. That means we would define a wave port. That's the point of excitation, right? So this is so the height of this waveguide, or you can see the height of this box, should be at least quarter wavelength at the operating frequency. In the second model, so this is the analytical model one. So we can also model it in another way. And in the second model, instead of using this PEC, PMC and wave port, we can use Floquet port and define master and slave boundaries. And definitely wave port will be replaced by Floquet port. And the height requirement is also same, lambda by 4, quarter wavelength at the operating frequency. So this is analytical model 2. One important thing is that you should de-embed the port right on the surface of the AMC. So you have to measure the reflected phase, or the reflection phase, right on top of the AMC. That's why we use this de-embedding feature. And as for the analytical model 2, this thing also applies. If you don't know how to de-embed the port or what does it mean, just bear with me. I will show you in the later parts of this presentation in HFSS. Hopefully that was sufficient for the time being in terms of theoretical understanding of AMC. Now let's move on to practical implementation of AMC structure in HFSS. This is the AMC unit cell that I'm going to design in HFSS. As you can see in this figure, we have got this AMC surface consisting of various identical unit cells. And this is the unit cell having a rectangular patch with a rectangular ring outside. And the substrate that I used is Rogers RT Duroid 5880 with a thickness of 3.15 millimeter. So let's design it in the HFSS and analyze the results. Okay, so this is the HFSS interface where we're going to create this AMC unit cell. So let's define the AMC substrate first. Let's define a new parameter, SL by 2, SW by 2, SL is 28.6 millimeter, SW is same 28.6 millimeter, and then SL, SW, and this would be the height of the substrate, which is SH 3.15 millimeter. Now let's define the material property. The substrate is Rogers 5880, so here you go, 5880. Okay, now let's define the ground plane. So this should be brown. Let's change the color and the dimensions as well. The dimensions should be exactly as the substrate. SW. Oops, it should be negative. Okay. All right. Now let's shift this local coordinate system from the bottom to the top surface of the substrate. So let's create an offset RCS, or relative coordinate system, and then create the bigger ring. So this should be our ring, Let's change the color. Let's define the parameter of the width as out P. So that is 24.5 millimeter. Out P by 2. Out P. Okay. Now we have to create another rectangle and subtract it from this original one to create the outer ring. So this would be our vacant rectangle. Let's define a new parameter for that. Let's say cut P 21.5 millimeter. Cut P by 2. Cut P and cut P. Okay. Okay, now let's select this ring and then rectangle 1 and then go to subtract and make sure your blank parts is ring and the tool parts is the rectangle 1, and that would create this rectangle or the ring. Now the time for the inner patch, let's name it inner patch. Let's change the color to make it more visible. And let's define a new parameter in P for the width of this rectangle. In negative in P by 2. And the dimension is 15.5 millimeter. Oh, I used double negative, sorry. Okay. In P, all right. There you go. Now we need to define the material property for the sheets. So ground, inner patch, and the ring, all of them are perfect E. So simply right click on it and go to boundary and then perfect E. This was for the ground, and for the inner patch and the ring we can define together as perfect E. Okay. So this is the physical structure for the AMC unit cell. Now we need to define the rectangular box, the radiation box. For that, go to menu bar and select this and simply create a box. Let's make it more transparent. Alright, now let's define the dimension of this box. It should be exactly what the substrate dimension is. And it's W by 2. And this box should cover the thickness of the substrate. So along the negative z-axis we must give negative of SH, and then it should be like this. The z-axis, the height of this box, I already talked about it in the previous slides, should be at least a quarter wavelength. That's the minimum requirement. This AMC works at 5 GHz. So at 5 GHz, I think 80 millimeter would be more than enough to satisfy the quarter wavelength dimension. So let me define a new parameter called box H for the Z and define it as 80 millimeter. All right. Okay. Now we are ready to define the master and slave boundary before defining the Floquet port. So in HFSS, before defining the Floquet port, we have to define master and slave boundary, not the radiation boundary. In order to do that, you have to go to Edit and then Selection Mode and then Faces. Select any of the face, for example this one, and then go to right click, Assign Boundary, Coupled Primary. So primary and master boundary are same. They're basically same, and the secondary and the slave boundary are same. So first of all, let's define the primary ones. We need to define the E vector. Make sure you select right exactly on the corner of this box. Don't select anywhere else. Not here, not here. Exactly on the corner of the box. And this big rectangular black dot will appear. Okay. That's fine. So that was the primary one, and now primary second, or the second primary boundary on this side. Coupled primary knee vector. Okay. So as you can see, this is the primary one and this is primary two. Now the time for the secondary. So this is the primary one. So on this exactly opposite side, you need to define the secondary boundary for this radiation box. Since I'm dealing with primary one, so need to select primary one. This is the corresponding secondary boundary for the primary one. And the E vector should be exactly along the same direction of the primary one, that red arrow. So make sure it's exactly on the same direction. You can keep it as 0, 0, no problem. All right, so secondary one is complete, primary one done. Now time for secondary two on this side. Because this is the corresponding secondary for primary two, so I need to select primary two from here. And then the E vector should be exactly along this red arrow. So make sure we are defining it along this direction. Okay. All right. Now the primary one, primary two, secondary one, and secondary two. Everything is done. Now time for Floquet port. The Floquet port should be defined on the top of this waveguide. Right on this plane. So go to Assign Excitation and then Floquet. The A and B direction should be selected manually from here to here, and make sure your B direction is along this edge of this waveguide. So need to define it manually. Okay. All right. Now this is the mode for Floquet. For example, you can give 10 Floquet modes in order to see the propagation at the higher order Floquet modes, and the attenuation constant will appear for those higher order modes. But for the time being, only two modes, the transverse electric and transverse magnetic. These two modes are sufficient for the time being. And this is the de-embed settings. We need to transfer this reference plane of measurement right at this Floquet port from this plane right at the top or right at the surface of the AMC. So we need to find out what reflection phase is occurring right at the top or right at the interface of the AMC and the air. That's why we need to transfer this reference plane or de-embed this Floquet port from this plane right on the top of this AMC. And the distance between them is around, it was box H minus SH. So box H was the height of the box and SH is the height of the thickness of the substrate. So if you click on the Floquet port, you can see the blue arrow, it exactly ends on the surface of the AMC. That means we're going to get the reflection phase value right on the surface of the AMC. This is very important, de-embedding. Okay, now we need to define the setup. Go to analysis and go to add solution setup and go to advanced. Frequency of the AMC is 5 gig around, so need to define 5 gig here. And the number of passes is 20, and maximum delta is 0.01. That would be fine for the timing. And the sweep is like, I need to see from 2 gig to like 8 gigs. And let's define 61 points. Fair enough. And save the fields. Okay. Now we can check the validation before running the simulation. Everything is fine. Now, before running the simulation, you need to save it. You can just save it in the documents as AMC. So this is our AMC unit cell. Analytical model with the Floquet port, with the primary and the secondary boundaries. Everything is fine. Now let's analyze it. So the simulation will run. It will take a little bit amount of time, and after finishing it, I'll be back. Alright, now the simulation is complete. Now let's explore the results. Go to results and create model solution data report. So from here you can see there are, in the S parameter, there are actually 4 Floquet port values. Basically this corresponds to the transverse electric and the transverse magnetic. So Floquet port 1 is basically transverse electric incidence, and Floquet port 1, this one is a transverse electric scattered or the radiated. So this one is 1, 2 is the transverse magnetic, and the first element is basically the incidence wave, and the second one is the scattered wave. So from here I need to see only the transverse electric mode for the time being. So just need to see it, select this one and go to angular degree and then just report. So here you can see it's very clear that it has an inherent S-shaped curve. We can determine the bandwidth from this plot. For example, if you want to find out the resonance, this is right exactly this point. You can zoom it and just place another marker. Okay, that's fine. So exactly if I want to find out the resonance frequency is 5.6 gigahertz of this MC. I can delete this M1. So this is the resonance frequency occurring right at 0 degree, 5.67 gigahertz. And as for the bandwidth, we need to take 2 points, plus 90 and minus 90 degree. So this is our positive 90 degree, I think, this point. So let's define a marker. 5.3, this is our F1, and for the negative 90 degree, it would be somewhere here. Oops. It should be somewhere here. Okay. So, all right. So the bandwidth is basically from 5.3 to 6.2, roughly 1 gigahertz. So this is our reflection phase of this AMC in itself by using the Floquet port. You can also simulate the same setup or the same AMC by using Analytical Model 1. Thank you very much for watching this webinar.